All right, welcome to the end. This one will be a little quicker than the other ones, probably. Okay, so we're going to look at some application problems in the book. Okay, we're going to start with your first application problem. This is on your homework assignment number 61. We have a fox population, and this fox population in some region has an annual growth rate of 9% every year. So in 2012, there were 23,900 fox out in the area. What is it predicted to be in 2020? Hey, that's me. Right? 2020. All right, great. So the idea here is that it's not going to be continuous growth, right? Especially if there's like breeding seasons or something. I don't really know about fox populations at all, but right, there's either a fox or not a fox. All right, so it's going to be this discrete growth. Then we have A as our starting value and B as our growth rate. Okay, and be very careful because it actually says, right, in the problem it says growth rates of 9% per year, but B is not 9. If B were 9%, right? If B were 0.09, that's smaller than 1, right? If it's smaller than 1, that's a decay rate. Okay? So it's not getting multiplied by 0.09. It's actually going to be 1.09, right? If I multiply 100 by this, we get 109. Good. That's a growth of 9%, right? So that's exactly what we do to start off here. This is number 61. Y is equal to A, our starting amount. Well, in 2012, you have to look at what our starting amount's going to be. In 2012, there were 23,900 foxes. That'll be our starting amount. 23, you can do 0.9 if you want to do things in thousands, or if you want to write 23,900, that works as well, times B, which we just said was 1.09. That's our growth rate to the X, right? Where Y is in thousands of foxes. X years after 2012. Okay, so if we say 23.9 is our starting, that's saying thousands. If you want to write 23,900, then you would just say, oh, this is how many foxes you have. Okay, but I don't like writing zeros. And then it's X years after 2012. So when X is 0, that's 2012. When X is 1, that's 2013. So 2020, that's when X is equal to 8. 8 years after 2012. All right. So all we have left to do is just plug it into our formula. All right. Plug that into a calculator, should get our answer. We'll round to the nearest fox. I don't want to have like 0.5 foxes. That sounds terrible. 23.9 times 1.09 to the 8. You get 200, oh my word, 208.4. And again, we don't want decimals here. All right. And this is how many thousand foxes there are. I guess 3 decimals could make sense. That's how many thousand foxes there are. So it's going to be 208,408 foxes. That's supposed to be an F. All right, I give myself an F on my spelling. Foxes, sort of. A lot of foxes. Exponential growth grows really fast. Okay? There are 10 times, almost 10 times, closer to 9 times as many foxes in 2020 if it's exponential growth. Now, what we're going to talk about later on in this chapter is different models that have to do with exponentials, because in reality, population growth is never exponential. It looks exponential, but it always kind of peters out. Okay? You can see this with a lot of population models of like cities and countries and stuff. Even though population growth is exponential, there are other things that affect our growth. All right. So that's what we have for 61. You also look at 62. All right. The 62 has a scientist, call it a mad scientist. This mad scientist begins with 100 milligrams of a radioactive substance. And that's decaying exponentially. Growth, decay. Okay, it's going to be decay. decay, all right? After 35 hours, only 50 milligrams remains. How many milligrams are going to remain after 54 hours? So we don't have an equation at all, right? We have a starting amount, right? We have a starting amount of 100, but we don't know our decay rate here. We know there is a decay rate, decays exponentially. We don't know it though. So let's write down what we do know. Okay, y is equal to a times b to the x. That's our exponential function. And we know our starting value, right? Originally we had 100 milligrams. Right? After hours, x hours. But we don't know our decay rate, but we can find it, right? It says after 35 hours, we had 50 milligrams. Let's write that down. After 35 hours, we had 50 milligrams. We need to incorporate that to find out what x is or what b is. So what we're going to have, right? That's our time. That's our x. That's how much we're going to have. That's our y. All right. So y is 50 when x is 35. We can find our b value right here. So divide both sides by 100. You're going to get 50 divided by 100 is equal to b to the 35th power. Whew. So if it were b squared, right, we'd square root both sides. If it were b cubed, we'd cube root both sides. B to the 4th, we'd fourth root both sides. So we're going to have 35th root both sides. But just like remember, right, square root of x, we can also use that rational exponent as x to the 1/2. Right, cubed root of x is x to the 1/3. So when we're taking the 35th root of both sides, we're going to write that as to the 1/35 power. Okay, 50 over 100, that simplifies to 1/2. Raised to the 1/35 power is equal to b. Type that into your calculator unless you are a madman with doing math in your head. You're going to get 1/2 raised to the 1/35 power is approximately 0.9804. Use 4 decimal points. Places. All right. We're going to get y is equal to 100 times b, which is 0.9804, raised to the x. That's our model here. That's our decay rate. Right? It's decay because it's smaller than 1. This mad scientist has this radioactive material that's decaying like that. But this doesn't answer the question. The question says, how many milligrams will remain after 54 hours? So that's really what we wanted after 54 hours. So my cat wants to play. I'll play with you after this video, okay? So after 54 hours, that's when x is 54. All right, so we get 100 times 0.9804 raised to x, which is 54th power. And oh my word, down. I need to type that into a calculator, and you're going to get how many milligrams are left over. If you type that in, 100 times 0.9804 raised to the 54th power, you're going to get 34.34 approximately milligrams. All right, and that's how much of the radioactive material is left. Okay, so thus ends the video, thus ends the section, and this guy over here, love. So that should take care of everything. But if you have any questions, you can always ask me. Slack, email, send me a message on Canvas. All right, and we will answer those questions. Okay, good luck. I said we. My cat will not be helping me answer these questions. Goodbye.